Need I say more? Howard?
Thank you.
Okay, I'll sit over here and do a little bit of the help with the Q&A if that's
okay. I'm Howard Darby, and I'm sponsored by Peterborough Associates, who, well, we used to call them engineering consultancy, but I think now modern parlance is development and infrastructure consultancy. Anyway, but they have just won the Consultancy of the Year 2014, so that's no small accolade. So anyway, they're kind of sponsoring me to do this research on embodied carbon, and the reason was because you want to be able to advise clients about the embodied carbon of their proposed developments, and at the time we really didn't have enough information to be able for us to be able to do that, so hence my involvement here. So anyway, first of all, just I'm going to mention something about defining embodied carbon, the timing of emissions, embodied and operational emissions, calculated by two different methods, and this is automatically going forward. Sorry about that. And finally, something to do with making sense of carbon factors. You're probably aware that there are a bewildering number of carbon factors for any particular material or component, so it's actually knowing which one to pick. So this is a picture of a typical building life cycle, where you start with extraction of raw materials, production of materials, construction, use with some maintenance, then demolition, disposal, whichever, hopefully reuse, recycle, recover, but obviously there's a lot of landfill and incineration going on as well. So this lot here, this little bit, the use, is what I'm defining as operational carbon, and the rest is the embodied carbon. And I think the thing to note about this is that this lot here, all the emissions from those processes occur in year one. The emissions from this use phase occurs for over 0 to 60 years, 0 to 100 years, or whatever, might be 0 to 30 years. And the emissions from these processes occur, at the end of life, which may be probably 60 years later. So one of the things I was concerned about was finding out if the emissions right at the beginning are worse than the ones at the end or during halfway through the life. So, and John was mentioning that we can increase the embodied carbon right at the beginning by heavy construction in order to save during the use phase, but it's knowing which is the best option. How can we weigh up the pros and cons of the two options? So I've developed this time factor curve, which is basically telling you that if you emit a ton of carbon, say in the year 30, during the building life cycle, year 30, it's the benefit of saving it. So start again. If you save a ton of carbon at year 30, it's only the same as 20%. It's worth 20% of a ton of carbon that you can save right at the beginning. Or say it another way, if I emit a ton of carbon now, it's 5 times as bad as emitting it in 30 years' time. So using that time value, it enables us to assess the benefits of expending emissions at any stage during the building life cycle. Now, this is made up of 3 components. One is the carbon intensity of the energy supply, and that is basically follows the profile of the UK government strategy for reducing carbon intensity of energy supply. It includes an economic discount factor, which is based on Lord Stern's assessment that it's going to cost a lot more to mitigate our emissions the longer we leave it. So the sooner we can make emission savings, the cheaper they will be. And then finally, there's an atmospheric CO2 decay factor, which is the factor which is used by British Standard 2050 when it's looking at emissions that occur at different stages in an assessment period of 100 years. So combining those three factors, I come up with the time factor, combined time factor. And I would just point out that I first produced a paper on this idea in 2011, and I noticed that September last year there's the government green, which it's a green book, the Treasury book on assessing public sector investment. They use a very similar curve, so I'm not actually claiming credit for that, but it's just interesting to note that they're following that course. So what does that look like in terms of the life cycle emissions of a building? This is a profile of a case study building I've looked at, which you have the years on the bottom and emissions as they occur here. This a large amount of the proportion, the emissions occur early on when you're producing materials, components and constructing the building, and then thereafter you get a gradual increase through the building use and intermittent refurbishments and refits. So that's in today's emissions. Now if you apply the time factor to it, you get, well, I'll just go back. The initial is about a third of the whole. But if you apply a time factor, you get a reverse effect where the initial is about 2/3 of the whole. So that's how I like to deal with the time factor in emissions. And there are, one of the things that I was preoccupied with in the research was trying to bottom out this idea of what are the proportions of embodied and operation. And there's two main ways of calculating embodied carbon. One is an input-output analysis, which is where you look at, it's a top-down approach where you look at all the inputs into the construction sector and then see what output they produce in terms of area of buildings and area of buildings. It's a quick way of working out your embodied carbon. It's not very process specific, it's all process specific, so you can't tell which processes or which part of the building is producing the most emissions, but it gives you a good overall picture of the relationship between embodied carbon and operational carbon. And the second method is the process analysis, where if you look at the traditional way of looking at each individual material and the processes to produce them into components, and it's a very lengthy, detailed analysis. It takes a lot of time, but it is very process specific, so you can see exactly where the emissions are coming from. And studies done in Japan and Australia indicate that an input-output analysis, well, in their cases, has shown that Embodied is up to 55% more than they had from process analysis. So I've looked at the UK and done the economic data for the UK and come up with an input-output analysis of housing, retail and office, and you can see here that this is a proportion of the whole carbon, the range of embodied carbon as a proportion of the whole carbon. So for housing, without a time factor, it's between 20 and 30%. With a time factor, 40 to 55. Retail, 25 to 50, etc. And the reason there's quite a range here is because there's quite a bit of uncertainty in the economic data. So that's why they get quite a big range. I think we're also going to say about this slide. Is that it? So the next slide gives details of a process-based case study of the Carrington building on this site, which I've done, and this shows that without a time factor we had 46%. This is the EC, this is the embodied carbon, 46% split between 16% was for structure, 18 architecture, 4 facilities and 8 for services. And if we look back here, so remember that figure, 46%. Offices, 46% is within that range. So that's quite nice to find. And then if I if I use the time factor, the total embodied is 67% of the total, and the structure becomes 29%, civil 7, services 9, architecture 22. So looking back, so remember the figure 67. 67. So I'm in the range of that. The office input-output analysis with the time factor. One interesting thing to note about this is that the structure actually gives you quite a high proportion of the whole life carbon. So you could say that the first thing that strikes me, because I'm a structural engineer, the first thing that strikes me is that if we can reuse the structure of buildings, refit them, refurbish them, then you're going to save a lot of carbon rather than building a new one. I mean, we might not like this as consultants, might not like to push that point, but I mean that is something that actually stands out quite clearly there. Right, so finally, this is basically what I called it, to getting the numbers right. If you've ever tried to look at what is the carbon emissions for say a ton of steel, you're faced with sort of like quite a range of numbers. Anything from this environmental product declaration from Celsa Steel in Spain, which gives you a value of 670, to steel construction industry, which tells you it's 919. The ICE database tells you it's 2210. And first thing you've got to remember is that this is actually just for crude steel. It isn't for your fabricated piece of steel. So you need to, if you're looking at an embodied carbon piece of steel in a building, you need to include the processes in between here, which brings up the emissions for a fabricated piece of steel to this value. So these are my research results. And so the first thing to notice is that there's a difference between fabricated and basic steel. And then the scrap content has a big impact on the embodied carbon of the steel production process, if you like. If you see that Celsa Steel use 100% scrap in their steel production in Spain, which is fantastic, excellent. I'm really pleased about that. But unfortunately, there's not enough scrap to go round. Can I go on a bit? 1 minute, okay. So there's only, of the feedstock into the steel making process, globally 37% is recycled. So we can't all have 100% recycled steel in our buildings, and if you bear in mind that Spain produces less than 1% of global steel, this isn't really very representative. The second point I want to bring out is this steel construction industry figure, which includes the end-of-life recycling, which, if you look at the emissions for the production of a ton of steel with 0% scrap, 19% scrap, and 0 to 100% scrap, you can see that the production emissions are reduced accordingly. And this is because you're feeding in scrap at the upstream end. What the steel industry tell you is that at the end of life, you're going to recycle at least 85% of that steel, and therefore I'm going to take account of that recycling benefit right at the front end. So I'm going to take off, this is my recycling benefit I'm going to get, but actually it's not going to come until 60 years' time. I'm going to take it off that, and I'm going to say this is the value that you should be using. So you can see here that this is my value that I've worked out. This is using their methodology, which is the benefit, and that's the figure that they're telling us we should use, which is about 900, which is exactly what was on that previous slide. So I'm confident my numbers are right, and what they're telling us is that we should bring forward that benefit right to upstream end. But of course, the problem with doing that is it's actually not available for the next cycle on, for the next building. And if you do take it there as well, you're double counting the benefit. It doesn't tell you when the emissions occur in the building life cycle. It's making you think that you're only emitting that at year 0, when in fact you're emitting that. So it's misleading, and that's about all I want to say really. But that's one of the academic roles perhaps we can play, is actually scrutinising industry figures. And with that, I better step down and hand over to Mark.
Just before you do, Howard, just if there are any immediate questions, I know there was a lot in that presentation. I found it absolutely fascinating, this discounting concept to kind of revalue future carbon emissions, which of course really